Hello, I'm Alison Pawley. I'm the geochemistry pathway cohort tutor. So geochemistry is basically using chemistry to understand geological processes. So these could be processes that occurred in the ancient past or processes that are occurring today. They could be processes occurring on the surface of the earth or deep inside it. And there's a lot of overlap between the geochemistry pathway and the other earth and planetary science pathways. Perhaps one of the main differences, though, is in the nature of the third year dissertation. So in this talk, I'm just going to show you a brief example of the sort of thing that you might do in the geochemistry project or dissertation in your third year. If you're doing a 4-year degree, you might do something similar in your 4th year, or you might do something similar in your 4th year on one of the other pathways. And of course, if you're a geochemist, your interests might go in a completely different direction. Okay. Right, so the Soufriere Hills is a volcano on the island of Montserrat in the Caribbean. It's an arc volcano, so it's on a destructive plate margin, and such volcanoes are very hazardous because they typically erupt in highly explosive eruptions. That's due to their high water content causing these massive explosions. But this volcano hadn't erupted in recorded history until 1995, when a big explosive eruption began and lasted for several years, forcing the evacuation of most of the island's population. So here you can see where Montserrat sits in the Caribbean. The volcano has been studied in many different ways, so using real-time monitoring, such as the sort of thing that Brendan was talking about, also looking at seismic activity. It's a really well-studied volcano, so it's also, there's been a lot of work looking at the products of the eruption after it erupted, and geochemistry is one way to look at these. And we've used it to give us an insight into the conditions inside the magma chamber before and during the eruption. So here on the left is an example of a bomb that was ejected in the explosive eruption. And this was collected by one of our PhD students who visited shortly after the eruption. And you can see that there's a lot going on in this sample. There's some dark grey blobs here, a few centimeters across, surrounded by a lighter grey magma, which has got some black crystals in it, and some white crystals as well. There's a lot going on here. It's quite hard to see in a hand specimen. So what we do is make a thin section of the rock. And up at the top here, you can see an example of a thin section. Now, these are so thin that minerals like these black minerals become transparent and brown in the thin section. And we then can look at these under the microscope to get a lot of detail about what's going on inside these rocks. And here's an example of the kind of microscope that we've got. A lot of these in our department, and all different degree pathways will use these microscopes. You'll start right at the beginning of your first year, and if you're following earth and planetary science pathways, you'll use them all through your degree, because you can get a lot of information about all sorts of different kinds of rocks. So not just volcanic rocks like this, all sorts of rocks under the microscope. So here's just a snapshot of the sort of things that we can see in these Soufriere Hills volcanic rocks. And these photos were all taken by our students. And here, each of these photos is showing a crystal in the magma. They're all about 1 millimeter long. So you can see there's a lot going on, even on this small scale. I just want to focus for now on the fact that all of these crystals have got rims around them that are slightly different from their cores, or in some cases, very different. And these rims are telling us something interesting here. So what are they telling us? Well, the core of the crystal must have formed first. So that's formed whilst the magma's sitting inside the magma chamber, slowly cooling over hundreds, maybe thousands of years. But then something's happened to this magma to allow these different composition rims to form. They formed just before the eruption. Their composition is different from the core, so the conditions in the magma must have changed just before the eruption for these different rims to form. And if we want to quantify these changes, we need to look at these samples in even more detail, and we need to analyze the compositions of these crystals. And this is where the real geochemistry comes into it. And we can analyze these compositions using an electromicroprobe. So we have one of these in the department, and many of you would use this in your third year or fourth year projects. And so here's my final slide showing the sort of data that comes out of the electromicroprobe. So here on the left is an example that one of our students collected a couple of years ago of a mineral composition. So this is from the core of one of these crystals. And because the mineral chemistry obeys the simple rules of thermodynamics, then we see that this chemical composition is very sensitive to temperature because of these simple thermodynamic rules. Also, aspects of it are sensitive to pressure as well. So that enables us to calculate the temperature that it was formed at from its composition. And we can see that from this particular example, this particular crystal, the core temperature was about 770 degrees. The rim temperature was about 830 degrees. Now, this might not sound like a very big difference, but it's interesting because the rim is at a higher temperature than the core, and usually rims form at lower temperatures than cores. So this is telling us that the magma was heated shortly before the eruption. And this is just one little bit of information. We can use other information as well. For example, these darker grey blobs, other geochemical information analysis tells us that they were formed at a higher temperature than the surrounding magma. And putting all of this information together allows us to interpret that what happened just before this eruption was that this darker, higher temperature magma was injected into the magma chamber, mixed in with the magma that was already there, raised its temperature. This produced the new rims on the crystals, but more significantly, the raising of the temperature caused all the water in the magma to be degassed, and this produced the explosive eruption. So our students are able to look at these very small scale bits of information and detailed geochemistry on a small scale to help interpret large-scale geological processes. Okay, so that's all I want to say. Thank you for listening.